Hello everyone, my name is Aarti Singh. I'm a PhD student in the ESC department at Washington University in St. Louis, and today I'm presenting a collision prediction method that is evaluated using ultra-wideband ranges and inertial measurement data. I will begin by talking about the motivation behind this work. This originated from the field of sports, but is applicable to many other domains that have motion or movement involved, such as self-driving cars or drones. As you would expect, whenever things move without having any sensing capabilities on them, they will collide into each other, be it robots or athletes. Now, it is not known exactly how many drones collide into what things, but by looking at the sheer number of drones increasingly getting sold each year, it can be expected that some drone is getting collided with something right now. Moreover, a more apparent and severe statistic is of around 3 million concussions that are sustained by the American football players alone. Now, traditionally and more commonly deployed solutions to avoid collision between objects are based on sensing the environment first, using cameras, lidars, radars, sonars, etc., and then processing the information, which might include hefty computer vision algorithms for image-based solutions, and costly equipments for sensing and data processing. Also, these systems depend on the physical properties of the objects and of the environment. As in, they might not work in foggy, misty, or rainy days. Instead, we plan to use a system that is built on ultra-wideband radio technology that is robust against such physical limitations of the previously mentioned methods, but at the same time has a very reduced cost of operation. So in this work, we propose a solution that uses ultra-wideband radio technology to get accurate timestamping in order to get internode ranges between any number of mobile objects in the environment, thereby making it a range-based solution. We then use these ranges to find relative position of each node in the environment. It should be emphasized that our problem statement of collision prediction only requires the relative kinematics, that is position, velocity, and acceleration of the nodes involved. Typically, in a range-based solution, the research that has been done includes anchors, infrastructures, or known location nodes that are used to get exact location of every object in the environment. But since our solution only requires relative position, it gives us an advantage to not worry about absolute kinematics, that is position or velocity or acceleration of the objects that are moving. This frees us from having to deploy infrastructure in the environment before making any sort of collision prediction. Another advantage that our method has that it is not centralized. Typically, a central processing unit gathers and processes all the information to do localization. But in our case, each node can do relative localization and make predictions independent of, independent of requiring a central processing unit, thereby achieving true autonomy and providing independence to each object involved in motion. This also, as you can see, will be more cost effective and communication effective, as we don't require bandwidth to first transmit all the information to the central processing unit and then passing the localization information to each mobile unit involved in the environment. So how does it work? In any environment, you can imagine there are multiple objects, and these objects are capable of conducting any variety of motion. it can be straight, it can be curved, and it can be relative, as in one car can be moving and another one could be just stationary. I'm representing cars in this scenario, but you can imagine it to be anything, any object that moves. What we plan to do is we plan to incorporate a tag, an ultra-wideband radio on each of these devices, which is capable of doing a two-way packet communication, and we obtain ranges from a pair of these objects. For simplification, let's imagine that originally two cars are at these distances, and over time they come closer, and we obtain distances during all this time. We create a matrix, and the matrix composed of a certain number of certain instances in time, and it is built for all the pairwise objects that are present in the system. We then build a cost function which is minimized such that the ranges are preserved. To some of you, this might look like this might look like something to what you have already seen. This is very similar to the classical MDS problem, where we have data points in high dimensional space that can be projected to a lower dimensional space while preserving the dimensionality. Sorry, while preserving the dissimilarity, I'm sorry. So what we do is we take these pairwise ranges and we obtain these xi's and xj's. This is usually done through an iterative process till we reach convergence. In our case, we don't just focus on preserving the dissimilarity. We tailor a new cost function, which is, as you can see, presented by S here. And this includes the ranges that we get from the ultra-wideband measurements, as well as the acceleration that we get from the IMU that is attached to each node. So this is a new cost function that we minimize for each node that is present in the system. And once we have minimized this thing, we are obtained with the position estimates for each node in the system. This process is named as SMAKE-OFF, which is scaling by majorizing a complicated function. The function in question here is our function, the SI, which is not very easy to visualize and is even more difficult to minimize since there is a square root term here. So we use SMAKE-OFF to minimize this function and obtain the position estimates which are relative for each node. Once every node calculates this minimization and obtain the relative position estimates, it transmits those position estimates to the nearby neighboring nodes, and the process is repeated for every node till we collectively get a reduced cost function. But that is just a stage for localization where we get xi's as the final result. Just relative position is not enough. Just relative localization is not enough. We need to predict what's going to happen in the future. So what you can imagine is that every node has something called a reaction time. What we propose is that if within that reaction time into the future, another object is going to come close to one said object, we call it a collision. If not, it is no collision. So if you imagine that the white car, which is a future position of this black car, we predict where the car is going to be into the said reaction time of this car. And if that future position is within the safety threshold or safety distance, which we considered safe, then we'd say it's a collision. Otherwise, there is no collision. So this case is going to be a collision. However, this case, we are going to say there is no collision. So that is a rough idea of how the algorithm works. We conduct multiple instances of these scenarios, and we use ultra-wideband radios to conduct the experiments. To mimic the motion, we use a commonly available Roomba. On the left-hand side, leftmost side, you can see there is the radio tag that we use. It's called a Sitara ultra-wideband radio. It uses decawave it uses a decawave chip, and for the transmission of nearby ranges, we use a narrowband transmission on top of it. This safely sits on top of a Roomba, and we have an IMU that is attached with a Raspberry Pi that is used to control the robot, as well as provide us with the IMU measurement. And in the rightmost side, you can see there are multiple such objects. They roam around in the environment with a fixed trajectory. Here I've tried giving a summary of the 3 set of clean experiments that we conducted. In all these experiments, there are certain nodes that are sitting stationary. There are certain nodes that are moving. There are multiple types of motion. The most significant one is test 3, where we have one node sitting, where we have one node moving, and the rest of the 3 are sitting, which achieves 4 different style of relative motion. So I will briefly talk about the result as well. This is a comparison study with another range-based method, which I have tried giving a reference to. It's called FACT. We use another collision prediction method. And in this figure, you can see there is a ground truth, and then there is estimates that are obtained by FACT, as well as our algorithm, which is autonomous collision estimation. We call it ACE. And in the most prominent scenario, which is the circular motion one, you can see that the FACT algorithm not only has worse error rate in terms of how accurate the location estimations are. In the future, it never really tries to follow the circular trajectory. Whereas ACE, which is our current algorithm we are presenting in this work, the error is very low, as well as the direction of the motion is preserved. So what that means is that ACE can follow this trajectory, versus the algorithm that we used as a comparison study was not able to. And this provides us a very significant outcome, that in all these scenarios, ACE was collectively able to get a very significant decrease in the error, whereas FACT, as well as the traditional MDS, which used the relative localization, was not able to provide any significant improvement. So FACT performed worse than MDS, and then ACE performed better than MDS. So in all these 3 scenarios, we have outperformed the traditional method and the new method. So there is a significant improvement to see here. That was in terms of localization. In terms of collision prediction, FACT is outperformed by our ACE method, whereas there is another traditional method called pairwise regression. And you can see our method, as well as FACT, although outperforms it, our method is much more significantly improved compared to pairwise and as well as FACT. So based on this, we have around 98% accurate collision prediction capabilities. And if when we have deployed it in these scenarios, in these experimental scenarios, we have achieved good results, and we do see it getting improved in the future as well. So yes, this. If you have more questions, I would like to take. I would like to open the floor for questions. But otherwise, thank you for listening to me.